Okay, so here we go with the exam 2 review for this is summer semester 2023. And we're looking at the exam 2 review for Math 234, which is multivariable calculus. All right, introductions out of the way. Let's do this. So much ado. Okay. So first thing we're going to look at, finding the domain and the range of a multivariable function. So the one that we're going to be looking at is the natural log of 4 minus 4x squared minus y squared. And we want to start by looking at the domain. And then once we've got our domain figured out, we'll move into the range and then talk about what the level curves of this function look like, as well as some general advice on how to establish what a level curve looks like for a generic function or some other types of functions, I should say. So when it comes to domains, there are only 3 rules that we really need to look at right now for specific functions. And those are going to be as follows. Number 1, I'm going to need a little more space than that. So how about we slide this way and up here. Rule number 1, don't divide by 0. Rule number 2, don't take the square root of a negative. We won't really be looking at the complex numbers in this course. We're sticking to the real space and real 3 space. So there's enough going on with our 3 axes already that we don't need to introduce complex numbers. So our domains will always deal with real numbers, meaning we won't be taking the square roots of negative numbers. And I should actually add one extra idea in here. So don't take the square root of a negative. So the easy way is just say don't take the square root of a negative. But what we really mean is don't take the even root of a negative number. So 4th root, 6th root, 8th root, anything like that, those are also all out. Odd roots are totally fine because we can take the odd roots of negative numbers, but not an even root. So usually our shorthand is say don't take the square root of a negative number, but really that means don't take the even root of a negative number. And finally, our third rule for our generic set of rules is going to be don't take the log of a non-positive. Of a non-positive. You might be wondering, well, why'd I say, is there a difference between a negative number and a non-positive number? And technically, yes, slight difference. And that's about whether or not we're including 0. So 0 is something that we can take the square root of, but it is not something we can take the log of. So taking the log of 0 is bad, but square root of 0 is fine, which is why we use negative versus non-positive. Might be a bit semantic there, but it ends up being kind of important. So those are our 3 rules. A couple more that do sort of get added in there when it comes to the domains of some trig functions, namely every trig function except for sine and cosine. So tangent, cotangent, secant, cosecant. Those also do have some restrictions in their domains, but they still fit under the rule number 1 of not dividing by 0. So you just look at the denominator of whatever that trig function is, and any spot where the denominator would be 0 is something that we have to take out of the domain. Outside of these 3 rules, we're going to assume that our domain is all real numbers, and then we'll just deal with any of these restrictions when we need to. Additionally, we'd have some domain issues with the inverse trig functions, but we aren't going to be paying a ton of attention to their domains in this course. But it is another function that we do know about that has a funny domain. Okay. So let's look at our specific function. We've got, again, the natural log of 4 minus 4x squared minus y squared. Ignoring the middle for a second, our function from an outermost level is a natural log function. So our rule that's at play here is that we need to not take the log of a non-positive number, which means whatever's on the inside of that logarithm needs to be greater than 0. So 4 minus 4x squared minus y squared must be greater than 0. Solve that thing around, and we end up with 4x squared plus y squared is less than 0, or less than 4, excuse me. Let's try again. There it is. We'll just move those two negative terms over to the other side, and then also I've swapped the sides that they were on, meaning that the inequality sign needed to change its direction. But I end up with 4x squared plus y squared is less than 4, which means I'm looking at the interior of an ellipse. So that 4 on the 4x squared means it's an ellipse instead of a circle, but a very similar looking shape. So again, because it's less than 4, I want just the interior of the ellipse, which is graph C. So that's going to be my option here. That'd be my domain graph. Quick distinction between C and B, so Bravo and Charlie, because they do look very similar. But the difference between those two graphs is that graph B, graph Bravo, is including its boundary, right? So it's including the ellipse itself. So that graph, the domain graph in Bravo, is 4x squared plus y squared is less than or equal to 4, where we needed strictly less than 4, is why we choose C instead of B. We do not want to include our boundary because anything on that boundary is going to mean that we're taking the natural log of 0. And that's not great. So we don't want to do that. We'll take option C, as in Charlie. So if that's our domain, now we got to go find our range. So let's start by looking at the range of our function, just ignoring the multivariable part. We have a natural log function, so I want to just look at a natural log. Let's just call it f of t is the natural log of t, right? Just the most basic natural log function I can think of, or which is its base form. The natural log has a range of all real numbers. So the standard natural log function with no transformations to it, no funny inputs, it's got a range of all real numbers. And this is if t is in the domain 0 to infinity, non-inclusive on both ends, which we know that from the previous part. We just looked at the domain. So we want to start with a range of all real numbers, and then pare that down based on the specific function that we have. So looking at the interior of our natural log function, we can get as close to 0 as we want, because that'll be right up to the edge of that ellipse. But the inside of our natural log function has a maximum value. So the max of 4 minus 4x squared minus y squared, which again is our interior piece, is 4. And it'll occur at the origin. It occurs at 0, 0. Because I've got 4 minus 2 square numbers, I'm taking 4 minus 2 positive numbers. This thing has a maximum value at 4, meaning that the range of our function, no, do it this way, meaning that the range of our function of x and y, rather than of t, is -infinity up to the natural log of 4. This time we will include that number, so a bracket at natural log 4. Because the interior, the inside of our natural log has a maximum value of 4, our range has a maximum value at the natural log of 4. So that's what we put in. And again, we're including natural log 4 because that point is allowable in our domain. That a point occurs, or this value occurs at the origin. The origin is definitely inside our domain. We can plug in 0, 0, and we get natural log of 4. So we choose to include that in our range rather than not including it. Back up to the top. I realized I wanted to mark that piece again. It's highlighting it's the interior of the natural log. And the final thing that we want is figuring out what the level curves of this thing look like. So what I would like to do is probably give myself a little bit more space. So maybe make that a touch smaller. Maybe compress it that way some, slide it a little to the left. Cool. So I'm going to sneak this equation in between that drop-down box that I've pasted in over there. So setting what our level curves look like based on the options provided. Lines, parabolas, circles, ellipses, or hyperbolas. So let's take our function, which our function, f of x and y, can be thought of more as a z equals a function of x and y, because the function value that we get out is going to be the z value. These are going to be going up or down the z-axis, so above the xy plane, I suppose, or below the xy plane. So I want to think of my function value, or my function's output, as a z value. And if I'm looking at the level curves, I'm looking at a specific value for z, so some constant value for z. I'm going to call it k. So k is going to be equal to the natural log of 4 minus 4x squared minus y squared. And really the only variables I'm particularly interested in here are x and y. Z is going to be just a constant. So I want to put this into some equation where I can recognize the x and y components being equal to some other number. So solve this thing out. I'm going to get e to the k is equal to 4 minus 4x squared minus y squared. Solve this thing over. Again, I'm going to put my x and y on the left side because that's where it just makes the most sense to me. It's equal to 4. Oh, hey, 4 minus e to the k. As soon as my pen decides it's going to work again, there it is. 4 minus e to the k. And here's where I'm going to have a little trick that I'm going to use. So remember that k is just a constant, right? It's a stand-in for z. It is some z value, but I'm choosing it to be a constant z value, which is why I'm looking at specifically level curves. So that number is just a constant, meaning 4 minus e to the k is still a constant number. So that whole expression on the right side is a constant number. Don't much care what it is. I'm not thinking of it as a variable. I want to think of it like it's a number. And then look at the equation, 4x squared plus y squared equals k. 4x squared plus y squared equals a constant number. And I recognize that equation as an ellipse, meaning the level curves of this function are an ellipse. The fact that e to the k came in, that exponential e piece over there, doesn't really play a big role in determining what this shape looks like, because again, just comes out to a number, not an exponential function. So this thing looks like an ellipse. So a few other common equations that it might be worth looking at to know what its level curves are going to look like. So starting here on the right side, so as I can zoom in on them. So I think that circles and ellipses are relatively easy to identify, right? It's always x squared plus y squared equals a number. And if we've got coefficients on those x squared or y squared terms, then it's going to be an ellipse instead of a circle. But other than that, those two I think are relatively straightforward to recognize. So the other three that we'll want to look at are lines, parabolas, and hyperbolas. So hyperbolic and parabolic functions. So lines, pretty straightforward, linear y term, linear x term, there'll be a constant that floats around somewhere. And we'll want to get this thing down to a y equals format, because that's the easiest way to recognize lines. Parabolic functions, we're always going to have one square term and one linear term. That's the hallmark of a parabolic function. It's like y equals x squared, or we could have x equals y squared. Doesn't matter which one's squared anymore. Not that it ever really mattered, but we're getting further and further away from parabolas must be y equals x squared the more math classes we take. So yeah, parabolic function, one square and one linear term. Hyperbolic functions tend to have a couple of different forms. So the hallmark that we'll see with hyperbolic functions is that they have linear asymptotes. Is usually what we look for in a hyperbolic function. And we have a couple of versions of those hyperbolic functions. The one that we've looked at quite a bit in some other examples and some other like web work problems we've seen is that one on the right, x squared minus y squared equals k. So pretty similar to a circle, except that it's x squared minus y squared instead of x squared plus y squared. But also functions like y equals 1 over x, those are hyperbolic as well. So whether that's 1 over x plus k or just k over x, either way, those will show up as hyperbolic functions. So this is what they'll look like once they're solved nicely. You might be given one that isn't solved as nicely because it's already set for z equals something, and you'll just have to rearrange it to make it look like one of the equations that you recognize. So let's look at a few of those examples. These ones I've already done out. I don't want to spend too much time going over all of them, because again, every time we're trying to find a level curve, we're just going to set our equation equal to k, or just any constant number. Again, z will just be a constant, and then solve it out until you have an equation that looks familiar to you. So x plus 1 over 3x plus y doesn't really look like any of the things we just looked at, right? Because we'll have to start from there and get it to a form that we recognize. Don't recognize it yet, so we'll solve some stuff. So again, z is equal to k, or a constant letter of your choosing. And I'm going to solve this thing for y. I'm choosing y just because there's only one of them. Seems like the easiest thing to solve for. So I'm going to try to get y by itself. Multiply our denominator over. I get y is over there. Divide k over. I can then subtract a 3x over. And then combine some things around a little bit. But I end up with that next line down. Y is equal to 1 minus 3k times x plus 1 over k. But in the end, this is y equals mx plus b, right? So it's got, using that k in there, it ends up in some other places, but remember that it's just a constant. So I could take this 1 minus 3k over k and call that expression m, right? Because that's what my slope would be here. And then 1 over k is my b value, my intercept. But that thing ends up looking like a line. Does not look like one at the beginning, right? It's got some rational function is equal to z. So a whole bunch of big mess going on there. But if we set it equal to k and then solve it until we get an equation we recognize, we find that those level curves are lines. So let's try another one. Oh, and well, spoiler alert, but the answer's already on screen. I start with the function x plus y squared. So doesn't really look like a line at the beginning because I've got that square element in there, but that's z being equal to x plus y squared. I want to solve this so that it's y equals something in terms of x, or maybe x equals something in terms of y. So I'll set it equal to k, get the square root of both sides, which gives me plus or minus k, which again, just plus or minus a number, meaning that y is equal to negative x plus or minus some number, which is a line still. It's got a slope of -1, an intercept of plus or minus whatever constant number I chose for z, but that now does look like a line in its final form. And then another example of a line. Apparently I'm favoring lines in some of these expressions, which probably means I think that we should know these for the exam. I think that's why I put them on here. But again, starting from an expression that does not look like a line, looks like it's an exponential function, but that's before we set z equal to a constant value and solve for y. So z is equal to our constant k. Solving for x or y means taking a natural log of both sides, getting down to natural log of k, so a constant equals negative x minus y. So again, y equals negative x minus some constant number, which means we're looking at a line again. Again, doesn't look like one at the beginning, but ends up getting there. I think this is our last example, but I've got my function f of x and y is equal to xy plus 3. So this time, if I want to solve for y, I'm going to need to divide by x, which means it doesn't end up looking like a line this time. So set it equal to k, because that'll be my chosen letter for z. Solving for y, subtract 3, divide by x, and y is equal to k minus 3 over x. So y equals some constant over x. And that's a hyperbolic shape. So that thing has hyperbolic level curves. Yeah, and that's the last one that I wanted to look at. So for the exam, just get comfortable with solving these kinds of equations to find level curves. Specifically, I thought that these 4 or 5 were particularly good to look at. Cool. So that was all a tangent off of just one problem. But again, if it's in the exam review, it's because I thought it was worth talking about. So that's why I did it. Okay, moving on. Next one down, tangent planes and approximations. So we are going to try to find the linearization of a function. It's another function in terms of x and y at the point 3, 0. And then we're going to use that linearization to approximate a point that's really close to 3, 0. So what we're going to do here, if we think about linearizations from back in Calc 1, a linearization was just finding a tangent line and then using the tangent line to estimate the value of a function near the point that the tangent line is centered at. So near the point where the line is tangent. We are going to evolve that idea out of Calc 1 and into Calc 3, where we still want to have that idea of a linearization, where we're taking some complex function and reducing it down to a linear approximate answer. But if we're stepping up from our old 2D graphs into 3-space, instead of a tangent line, we're going to need a tangent plane, which is what our linearization is. So if we think about the equation of a plane, we've got, an x term plus a y term plus a z term. And usually we say that's equal to 0 as long as we're subtracting away that center point from each piece. And from that tangent plane, if we solve it for z, that's going to give us the equation for our linearization. So linearization just is the tangent plane, but solved for z. So this L of x and y is really z equals L of x, y, just like we're using z equals f of x and y at the beginning of these multivariable functions. Because as long as we're going to be able to call it a function, that means we can write z equals a function of x and y. No particular reason it has to be z. It's just, starting off, z is the easiest one because it's our new axis. But we could also find functions that go along the x-axis or go along the y-axis. Our variable choices are arbitrary. So let's talk about this tangent plane. Highlighting some of the key elements that are going on here. This initial piece, f of xy, this is the center of our tangent plane, or rather, this is going to be the point where our plane is tangent to the function. And we get that just by evaluating the function at the point that we're given. So we have a center component, which again, where our plane is tangent to the function. And then we're going to have an x slope term, which means that we're going to need an x partial derivative, because that's what will give us the x slope. And if we have an x slope, we should also have a y slope, which is what the other piece is. So in the end, our linearization is made up of a center, some sort of center point, which is where our plane is tangent. And then we're going to add in an x slope term, and we're going to add in a y slope term. So we'll need an x partial and a y partial to make this linearization make sense. So let's get that process underway. I'll start with that x partial. So f partial x means I need a derivative of the square root of x plus e to the 8y minus 3. That derivative should look like 1 over 2 times the square root of x plus e to the 8y times the derivative of the inside with respect to x, which that derivative is just 1. So our chain rule means we're just going to multiply by 1. I can then also evaluate that partial derivative. Let's go ahead and do that right now. So f partial x, I want to evaluate it at the point that I'm tangent to, so 3, 0. Which means this ends up looking kind of nice. I've got 1 over 2 times the square root of 3 plus 1, so I have e to the 0. 3 plus 1 is 4, square root of 4 is 2. 1 over 2 times 2 is 4. So 1 over 4 is my x partial. Let's also get ourselves a y partial here. I'll bring the, it's a little bit out of the way. Oh. But if I'm going to get a y partial here, I know I've got the square root of x plus e to the 8y. So my derivative is going to be 1 over. There we go. I'll just slide it up a little bit so I can write a little bit more cleanly. 2 times the square root of x plus e to the 8y. And then I need to come through and multiply by the chain rule. This time it's a y partial. So the derivative of the inside is 8 e to the 8y. So I'll just multiply that in up top. Might as well also calculate the y partial at the point in question, 3, 0. That'll be 8 times 1 over 2 times the square root of 4 again. So 8 over 4 is 2. Let's slide that down a little bit because we also need to get regular f at 3, 0. All right, so just evaluate the original function at the point where we want to be tangent. It's the square root of 3 plus 1. Wait, hang on. Back to the original function. There's that minus 3 that's in there too. So don't get it twisted. Square root of 4 is 2, and then minus 3 is negative 1. So don't forget about that constant term when you're evaluating the function at that center point, at that tangent point. So now we've got everything we need. We should be able to calculate our linearization. And I'm going to take these parts, shrink them down just a little bit so I can keep everything on screen. Particularly that equation at the top, where I want L of x and y, which is my linearization, to be the equation of this tangent plane, just to solve over for z. So my center point I know was -1, so I'll plug that in, plus the x partial term, the x slope term. I have an x slope of 1/4, and then multiply that by x minus 3, because I want to center this thing at an x value of 3. Plus, I need my y partial term. I have a y slope of 2, and I'm centered at 0 on this one, so y minus 0. So that's the equation of my linearization. And now I want to use that linearization at a point that is pretty close to the point in question. So need a little more space even. So let me just slide that part down. I'm looking for L of, this was 3.3 and 0.01. So that is -1 plus 1/4 times 0.3 plus 2 times 0.01. Since those, like x minus 3 and y minus 0 is really just the distance that x and y are from the point 3, 0. So x is 0.3 away, y is 0.01 away. And then, yeah, we just plug all that in and get a number. I'm just going to leave it there. That seems fine. Color code those pieces because that's what we're plugging in. Cool. And that's our tangent plane, well, it's our linearization, which is really just a tangent plane. All right. Continuing in the realm of tangent planes, let's look at another one. So I'm going to take two parametric curves, an R1 and an R2, and I'm going to say that they both lie on some surface S, and they intersect at the point given, -2, -4, 2. We want to find an equation of the tangent plane to the surface S at point P. So some surfaces going on here. Don't really care what that surface looks like, but it's, some curved surface and curved 2D surface out in space. I've got two curved lines that are on the surface, on that surface, and they're going to intersect somewhere. My goal is to find the equation of a tangent plane. So if I want the equation of a plane, the easiest way to do it is to get two things. One is a point on that plane. We already have that. We want to be tangent at the point -2, -4, 2. So that'll be the point that we're going to use to find this plane. The other thing I need is a normal vector. So if I could find a normal vector, I'd have the equation of this plane. So that's what I want to do. Let's find the equation of a normal vector. And since I've got two curves already, two parametric curves, if I took their derivatives, I could get their tangent vectors. And if I have the two tangent vectors at this point, I could take their cross product to get the normal vector. So that's our plan. Our normal vector, I'll denote it in red, and we'll use n for normal vector. As soon as my pen decides to work again, hey, get out of here. And I'm going to say that normal vector is equal to the cross product of those two derivative vectors. So the cross product of those two tangent vectors. Man, this has gotten bad. Just check chat while I'm repairing my pen. Looks like we're good over there. Come on. There we go. So our normal vector, denoted in red, is going to be R1 prime cross R2 prime. That's our goal. We'll also need to make sure that we end up at the specific point that we want. Because right now we have our two curves parameterized for t and s. And we know what our point is. We know that that point P lies on both of those two parametric equations. So I should find a value for T and for S that correspond to this point. So if I look through those components, their X components are square. So I don't want to start there. Their Y and their Z components, those are both linear, but the Z component looks like it's the simplest component of the bunch. So what I'm going to do is take those two Z components and set it equal to the Z component or the Z value of that point to solve for T and for S. So I'm going to take negative T minus 1 is equal to 2. And I'm going to take S plus 6 and also set that equal to 2. So no particular reason I needed to choose the Z component other than it looked the easiest. I would not choose the X component because I'm going to get two solutions there because it's a quadratic term. But either the Z or the Y component would be easy enough to solve here. And in fact, you'll see if you were to take the values that we'll solve here in a minute and plug them into the X and Y components, you'll get -2 and -4 respectively. But enough ado there. T looks like it's -3 and S looks like it's -4. So highlight these values because I'm going to want them later. All right, let's get those tangent vectors, those derivative vectors we talked about. R1 prime of T is the vector -10T minus 4 for the X component, 3 for the Y component, -1 for the Z component. Slide over and also get R2 prime of S. And it is equal to the vector -6S 2, 1. let's just slide that piece over so it's on top of the R2 component. Because now I want to evaluate these tangent vectors at the 2 points that I solved for, or at the single point I solved for, but it's one's a t value, one's an s value. So I want r1 prime of -3, and I get the vector 30 minus 4 is 26, 3, -1, and then I need r2 prime at an s value of -4, and I get the vector, let's see, -6 times -4 is positive 24, 2, 1. Now that I've got my two tangent vectors, I should take their cross product to get a normal vector. So n, the vector we've been interested in this whole time, is equal to the cross product. Last chance. Okay. The cross product of I, J, K. 26, 3, -1. Then 24, 2, 1. Looks like I could slide that in just a little. Bring that down and calculate this vector. All right, let's see how good I am at cross products. For the x component, 3 times 1 is 3, minus 2 times -1 is -2. Up next, -1 times 24 is -24, and 1 times 26 is 26. Lastly, 26 times 2, that's 52, minus 24 times 3, that's 72. Oh, not again. There it is. Okay. Shrink that a little bit. Gets me to the vector. Actually, you know what? Unshrink me. Let's just write this down below. Okay, 3 plus 2 is 5 for our x component. Then -24 minus 26 gets me to -50. And lastly, 52 minus 72, I believe that's -20. So there's our normal vector. Now we just have to put this into the equation of a plane, which the equation of that plane, to give myself a touch more space, the equation of a plane, 0 is equal to the normal vector dotted with the position vector minus the point vector. What that ends up looking like is the equation 5 times x minus x naught, which was -2. So 5 times x plus 2 minus 50 times y minus y naught, which was -4, minus 20 times z minus z naught, which was +2. And that's the equation of our plane. We've got a point that we're tangent to, and a normal vector from the cross product of our parallel vectors, our tangent vectors. Let's see, how straight am I writing today? Not very. Oh well. All right, up next section that came after tangent planes, we had the multivariable chain rule. So this is a fun one. Looks like I forgot to erase a piece. So what do we want to do? So ultimately this web work problem is asking us to find the partial of z with respect to s and with respect to t. I'm going to do all of the first two parts, but then I think I'm just going to go get the s partial and call that good enough for now. The t partial will look much the same, just with the t partials plugged in instead. So the thing I'm going to try to get here is the partial z derivative with respect to s, dz over ds. And what that's going to look like, because z is a function of x and y, and then x and y are functions of s and also t, but we're going to ignore that part for now. X and y are both functions of s. When I go get the derivative of z with respect to s, I'm first going to need the derivative of z with respect to x, or rather the partial with respect to x. And because x is a function of s, I have to come through and use the chain rule to say when I take the derivative of x, I get its derivative term with respect to s that I have to multiply in later, multiply in after. But x is not the only variable that z is a function of, because z is also a function of y. So I'm also going to need a y partial term in here. And if I take the derivative of y, the chain rule says I need to multiply by y's derivative with respect to s. So that is going to be our goal. It's going to be four factors in total. So I need a zx partial, I need a zy partial, then I also need an x s partial and a y s partial. So let's start getting those individual pieces, and then we'll put them all together at the end. Starting with our original function z, it's the sine of negative 2x times the cosine of 8y. For starters, I just want its x partial. So the derivative of sine is positive cosine, and then the chain rule says I'm going to bring a negative 2 out. So this is negative 2 cosine of negative 2x times the cosine of 8y. Shrink that so that it fits in the box. Then let's do the same thing, but for y. This time I get to ignore the sine negative 2x part and just get the derivative of cosine of 8y. So derivative of cosine is negative sine, and then the chain rule says multiply by 8. So this will be negative 8 sine of negative 2x times the sine of 8y. Also, shrink that down so it fits in the box. So now we've got our x and y partials. So let's go through and get our s and t partials. Although really we're only going to need the s partials. So start me with the derivative of x with respect to s. X is s squared plus t squared. So that derivative is going to be 2s. And then y is 3 minus 2st. So that derivative there is going to be negative 2t. And again, since I'm just going to focus on the s partial, I don't actually need the t partials. So I'm going to save that. I'm probably come back and do that at the end. So I've got all the pieces I need now. So let's just start organizing them. So z partial s looks like this. It is the x partial, which is negative 2 cosine of negative 2x times the cosine of 8y. Close that part because that's all the x partial. Come through and multiply by the derivative of x with respect to s, which was 2s. That completes our first term. And I want to add to that the y partial, which was negative 8 sine of negative 2x cosine of, not cosine, sine, it's a derivative term, of 8y. There we go. And then we'll come through and multiply by the s partial. Specifically y partial s, which was negative 2t. Okay. So in its simplest form, in its first form, the clearest form, maybe we should say, this is what our derivative piece looks like. It's an x partial times x partial s plus a y partial times y partial s. So we don't quite have a coherent answer just yet because our derivative function here is still including x and y, which are both functions of s. Well, functions of s and t, but importantly here, functions of s. So I need to go back through that expression I just wrote down and substitute out all of my x's and y's. And that'll be my final step. So z partial s. One more try. Let's see what we get. This is negative 2 cosine of negative 2 times s squared plus t squared. Times the cosine of 8y, which means I've got 8 times 3 minus 2 st. All right, close that parenthesis, close the cosine parenthesis, and we still have our 2s term, our partial s term. So 2s. All right, all that gets us the x partial term. So now let's come through and in the line below, because I have out of space, minus 8 sine of negative 2x, which is negative 2 times s squared plus t squared. close that parenthesis, close the sine parenthesis, times the sine of 8y, 3 minus 2 st, close that parenthesis, close the sine parenthesis, and multiply by the y partial s, so minus 2t. Cool, and that whole line together, or those whole two lines together, make up z partial s. Quite a bit of writing to do there. But nice part about if we have to also get z partial t is that almost all of the work was done just to get this first partial derivative. So if I wanted to get the t partial instead of the s partial, the only bits that are going to change are those blue brackets at the end of each line. So everything else we did before that, it's all still going to work. We have an x partial that's still an x partial. We have a y partial that's still a y partial, or z partial x, z partial y. But those two blue brackets were the s partial derivatives. If I wanted the derivative of z with respect to t instead, I'd replace those blue brackets with t partials. Since I've been writing t in green, I'd probably change the brackets to green instead of blue to signify what I was doing there. So if we need the t partial, again, we would just replace those two blue brackets with the t partials instead. And those t partials would be 2t for the derivative of t squared, and negative 2s for the derivative of negative 2st. So yeah, if they came up, we just swap out those blue brackets for the t partials, and we'd have our answer. Okay. So that's the chain rule. So let's move on to the next section, directional derivatives and gradients. So as a quick sort of concept question or concept idea, one that might be a concept question on the exam, the gradient of a function is going to be a vector that points in the direction of greatest change. So it'll be showing us the direction where sort of a derivative term is the greatest. So think of the gradient like it's a kind of it's a kind of derivative term. We always operate the gradient on a scalar function. So we're taking a multivariable scalar function like f of x and y, and when we apply the gradient to that, our result is a vector made up of derivative components. So if we've got a surface that's out in 3 space, the gradient is going to be normal to the surface at every individual point. So it's not quite like it's part of a tangent plane, right? So it's similar to the way that we find, tangent lines when we look in 2 space, where, a tangent line gives us a parallel vector. This gradient is going to give us a normal vector, which again would be components of that gradient is a component, that normal vector is a component of a tangent plane. But again, gradient operator, it will act on a scalar valued function, and its result will be a vector valued function. So when it asks here for the max rate of change, well, we know that thing is in the direction of the gradient. Yep. And that max rate of change is just going to be the magnitude of the gradient. So turns out both of these pieces are going to end up involving the gradient. So we just look at the question as a whole, the two things that it wants, the max rate of change and the direction in which it occurs. So both of those are the gradient. So we just got the gradient itself. It would be the maximum rate of change pointed in the direction of the maximum rate of change. But this question is asking us to separate out the two pieces. It wants us to separate out the magnitude and the direction. But that's what it is. Top line is the magnitude of the gradient. Bottom line is the direction of the gradient as a unit vector. Let's highlight that element right there. We need to make sure that we enter a unit vector into that second box. So this one is just going to be a, back that up. So we just need to calculate ourselves a gradient here. We've got our function, f of x and y. So the gradient, which looks like del f, del being the upside down triangle operator, del f, which is the gradient, is f partial x in the x component, f partial y in the y component. And if we had a function of 3 variables, there would also be an f partial z in the third component. But this is a function of 2 variables, so it'll have 2 components. So we should calculate those. So negative x times e to the negative 3xy. The x partial is going to be negative e to the negative 3xy. I'll do this requires the product rule, so I'm going to do the derivative of x first, and then add on to that the derivative of the e to the x part. So adding on to that, I've got a negative x, but also if I take the derivative of e to the negative 3xy, I'm going to bring down a negative 3y from the chain rule. So in the end, this thing becomes plus, because it's plus a double negative, so plus 3y x e to the negative 3xy. And that's our x component. That's our x partial. We get our y partial, same thing, but derivative with y instead. We're going to bring down a negative 3x. So negative 3x times x becomes positive 3x squared times e to the negative 3xy. So that is our gradient as a function. We wanted to evaluate the gradient at the point 3, 0. So that gradient at 3, 0 looks like the following. So our exponent is 0, because negative 3 times 0 is 0. So that first piece is negative 1 plus 3xy e to the negative 3xy is 0 times 1, so plus 0. Because there's that y down in front. Makes the whole thing 0. That's kind of nice. Next bit's got a bit more going on. 3 times x squared. X squared is 9. Times 3 is 27. Times e to the 0, which is 1. So clean that up. Negative 1, 27. So that's our gradient vector. And again, we wanted the magnitude of that gradient vector as well. So magnitude of gradient f is the square root of -1 squared plus 27 squared. Throw a hat over top. So let's calculate what that thing is. 27 squared. I know this. 729. Yeah, that must be 27 squared. It's a multiple of 3. Cool. Yeah. So it's a power of 3, I should say. Power of 3. Right. So 27 squared is 729 plus 1 is 730. So that's our magnitude. And with that, we now have everything we need to answer the questions at the beginning. So the maximum rate of change is that magnitude. So it's 730. And then the direction it occurs in is the unit vector. And that unit vector is the vector we already got, -1, 27, divided by the magnitude. So divided by square root 730. And those are our two components. Or, well, rather splitting up our gradient into its two components, the magnitude and the direction. All right, up next, the meat of this exam section, maximum and minimum values. So we're going to be relating this idea back to the same idea that we had in Calc 1 of calculating maximum and minimum values. Back in Calc 1, we said that if we wanted to find an absolute maximum or minimum value of a function on a closed interval, that part's important, so a closed interval, that maximum or minimum value is going to occur at one of two places. It'll either occur at a critical point, somewhere in the middle, or it'll occur at one of the boundary points. In Calc 1, we only looked at intervals, which means we had a boundary point on the left and the right, so only two boundary points, and then also however many critical points we got in the middle. We're going to evolve that idea up into multivariable calculus, but the process will be pretty much the same. Instead of looking on a closed interval, we'll just look on a closed domain, so a closed region. So it's a two-dimensional region instead of a one-dimensional interval. But the same idea is going to hold true. If we're looking at absolute maximum and minimum values on a closed region, they're going to have to happen either at a critical point or at a boundary point. We're just evolving our idea of what a boundary point looks like, because now our boundary point could have multiple points in it. And in fact, we'll also need to look at critical points specifically along the boundary instead of just within the region itself, but it's the same thing. So the steps we're going to take here. Step number 1 for finding absolute maximum and minimum values is just finding our critical points. So find all critical points. This tends to be the easiest step. It's finding all the critical points. Step 2, similar to the first, we'll find all critical values on the boundary. And that's going to include our boundary points. I'm just going to make a note right here. Including boundary points. And then step 3, check all critical values. So step 3 is once we find all the critical points and all the critical values on the boundary, we just plug all of them into the original function the largest value there is our absolute maximum, and the smallest value there is our absolute minimum. So a couple of other points to talk about here. When we're finding all of our critical points in the original part, this is a two-dimensional problem, or it's a problem of two variables. Once we go to the boundary, it's only going to be a one-dimensional problem, or a one-variable problem. Meaning the boundary check that we do is going to be exactly reverting back to Calc 1 maximum and minimum values. So we start with finding all critical points within the region, which is a two-variable problem. Then we'll just look on the boundary, and when we're looking on the boundary, that should only be a one-dimensional problem. So the boundary of our region should just be a curved line, so some sort of curve in space. But again, should just be a one-variable problem once we get to the boundary. Which means that once we find the critical values on the boundary, we'll also have to find its corresponding x or y value. Because when we find our critical values on the boundary, we're only going to be getting one of our variables out of that check. So we'll need to come back and solve for the other variable as well. But okay, that's our plan. Critical points, boundary points, check them all, see what we get. So let's take a look at the function that we have. We've got x squared plus 4y squared minus 16y minus 2. And we want to be inside of this circle centered at the origin with a radius of 6. So x squared plus y squared is less than or equal to 36. Just think of that. That's a circle. It's centered at the origin. It's got a radius of 6. That's going to be our region. So the first part, which I tend to think is one of the easier spots to be looking here. Well, you know what? I have these colors backwards. Why don't we put you in blue, and I want to put you in green. I think that's usually the way that I think I usually do the boundary in green. Yeah, we'll find out. Okay, so finding those critical points. Step 1. If I want the critical points, I need partial derivatives for x and y. So f partial x, which, looking up at our original function, there's only one term that depends on x, which is nice. Its derivative is 2x. I'm going to set that equal to 0, which means I just get the solution x equals 0. Then slide over to get the y partial. F partial y. This thing is 8y minus 16 equals 0. So I get y equals 2. So I've got only one equation, or only one solution to each of the partial derivatives, so I'm only going to get one critical point. If we had more solutions to the individual partial derivatives, what we would do over here is, say, for example, I got 2 possible solutions for the x partial and 2 possible solutions for the y partial. I would then pair each possible solution from the x side with each possible solution from the y side, giving me 4 total pairs of solutions, 4 total systems of 2 equations, and solve each of those systems for their critical points. In this particular example, I only have one system of 2 equations. So I'm only going to get one critical point because that system happens to be linear. So the one critical point I get is 0, 2. 0, 2. I said 0, 2. Close enough. And that's step 1 complete. We have our critical points. Or critical point, because there's only one. Step number 2, I want to look along the boundary. So if I bring my boundary equation in, it's x squared plus y squared equals 36. And what I want to do here is substitute that boundary into the equation in some way. And here's the way that I like to think about this problem is this. I'm going to first explain it my way, and then I'll offer an alternative, because I know that my way doesn't always go over as nicely. But x squared plus y squared equals 36. I've just got that circle. I'm going to take my original equation, which was x squared plus 4y squared minus 16y minus 2, and break apart the 4y squared. I'm going to break it apart into y squared plus 3y squared. And then I'll still have my minus 16y and my minus 2. That's my function y. The reason I did that is so that I could have an x squared plus y squared show up right here. And then I can just substitute directly into that equation. X squared plus y squared I know is 36. So that's just the circle component right there. And then plus 3y squared minus 16y minus 2. I'm going to call this new function g of y, because I know that's how the web work usually calls it. So I want to stay a little consistent there. But this is my boundary function. Right, so the boundary along that circle is given by the function g of y. And importantly here, this is now a function of one variable, meaning it's just a 1D curve, one-dimensional curve. So that's the way I like to think about the substitution. Another way that you could have substituted here is because I've got that 1x squared in there and I'm trying to eliminate all of my x's out of the original function. I could have solved my circle for x, called it x squared equals 36 minus y squared. Notably here, though, I don't really want to take a square root because I don't want to deal with the plus or minus in this problem, as long as I don't have to. And because the only x term I have in my function is x squared, I don't end up needing to worry about that plus or minus, at least not yet. So I could have also just substituted for x squared, called it 36 minus y squared, then plus 4y squared minus 16y minus 2, and you should still get the same equation as me in this g of y step that I've got over there. So either method works. Either way, you should get to 36 plus 3y squared minus 16y minus 2. And then we'll solve from there. So we have our boundary equation from whichever way we wanted to get there. And now we need to find critical points on this boundary. So g prime of y is going to be the derivative of this mess, which should be 6y minus 16. And I want that thing equal to 0. So from there, solve this thing for y. I'm going to get 8/3. 8/3. Yeah, let's mark these in green. Yeah. Because these are going to be our boundary points. Hang on one second. Do I usually do the boundary in? I may have not been like overly consistent in which color I've been using in the notes on this one. All right. I'm just going to stick with what I got. For some reason it just looks a little odd to me right now. Okay. So we get our 8/3, and that's our y value. Like I said, we were also going to need to get the corresponding x values that go with it. So x squared, if we bring it down, we know that it's equal to 36 minus y squared. So 36 minus 8/3 squared, where I'm just going to be slide this a little bit further over, give myself some more space. Plugging that in right there. And then figure out what x is. 8/3. That means that x is plus or minus the square root of 36 minus 8/3 squared. Put the hat on our square root. And for some simplicity's sake, I'm going to round this number for now, just that I can get an idea of where this thing is. This is plus, green, plus or minus 5.3784. Meaning the two critical points I find on my boundary are plus or minus 5.3784 and 8/3. So I found two critical points on the boundary, and they are symmetric. They both occur at the same y value, but one of those is at a positive x value, and one of those is at a negative x value. So one on the left, one on the right. So I want to bring in a diagram real quickly. So I'm just going to grab that from the other part of the notes that I have. Okay. Looks like I'm going to need to do a couple of things here real quick. Slide down, give myself some more space right there. Grab those 2 points, make them green. Okay. Cool. Bring me back. Nope. Yeah, okay. I'm still right here. Take me back to these notes. Okay. So those are the points we found so far. Those are all our critical points. We also need to consider our boundary points, which is this diagram that I want to bring in here. So I've got a diagram of all the points I'm going to need to check in the end. I've got the critical point in blue that's near the center. That's the one I found in part 1. Those two boundary critical points I've got drawn in green. They're on the left and the right. I also need to look at the boundary values of my boundary equation. So because I've got to be inside of this circle, I need to look at the maximum and minimum values for y, because I'm looking at my boundary function as a function of y. So I need to look up at y's maximum value, which is 6, and its minimum value, which is -6. Because again, circle with a radius of 6. So those points along top and bottom also need to be considered as potential points where the maximum or minimum could occur. Cool. So these are the ones I've got. So if we think about kind of the way that this function is working, it is symmetric in the x direction, but we've added in a term that's kind of shifting things up in the y direction. So those, what would have been the critical points of like 6, 0 and -6, 0, so the left and right boundary points, if we're just looking at the edges of the circle, those points ended up getting shifted up a little bit to become critical points rather than just boundary points. So we don't actually need to be checking 6, 0 or -6, 0, because if we did need to check those, they would show up as critical points along the boundary with the way that we did the problem. So just 0, 6 and 0, -6 are our boundary points, those boundary values. So altogether, I've got 5 points. one critical point, two critical points on the boundary, and then two boundary points, one blue, two green, two red. Step 3 is to simply evaluate all of those values. And since this is mostly just a calculator step, I took the liberty of doing it ahead of time. So here are the values I get when I plug them into the original function. So the thing that I want to maximize or minimize is the original function. So I'm plugging it back in there. It's the very original function. I don't plug them back into the derivatives because why would I? I would just get 0 if I plug them back into the derivatives. So plug them in here, plug them into the original function. And then the biggest value is our maximum and the smallest value is our minimum. Cool. So looks like what we get here is that critical point was an absolute minimum, the one that we found in step 1. So that 0, 2 point, that's our minimum. We got a value of -18. And then our maximum occurs at one of the boundary points, specifically the boundary point at the bottom of the circle when y is -6. I got a value of 238 there. And then those critical points along the boundary might have been, those might have been, local minimums for the boundary, but I can find a smaller value if I look inside the circle. Cool. So that is our min and max stuff. All right, that takes us to the end of the multivariable function parts of this exam material. Now we're into the vector valued functions. So this is the stuff that we're doing out of chapter 16. So vector fields and line integrals. Once we wrap up those topics, that'll be it. So let's take a look at some of that stuff. Yeah, basically about on the time schedule I thought I'd be in, which is to say slow. Right. What are we doing? What are we doing here? Write down the given integral in terms of t. And I also thought it was worth here mentioning a formula that we may want to use. So that is the work formula. I must have written this down here because, again, if I wrote it down, it's probably because I thought it was important for the exam. So I think this is a formula you should remember for the exam, or at least know where to find in the exam. So work. If you've taken a physics class before, this will hopefully look pretty familiar. Work is the integral of f dot dr, where f is the force field and dr is the distance derivative vector, or the position derivative vector. If you've just taken the algebra version of calculus, and you're probably used to seeing the work formula as force times distance moved, so F times D or F times R. But the calculus version, where we might have a variable force field, is the integral of F dot dr, where the thing we're plugging into F is the position vector R, so that's why it's F of R of T. But again, that capital F is a force field, and that R prime is the derivative of the position vector. So I think that that's going to be important. So know that work formula, or again, just know where to find it. So what we're doing here is like similar to a work problem. It's just not called a work problem. So let's dive into it. So write down the given line integral in terms of t. So we've got y, the integral along a curve c ds, where ds is an infinitesimal move along the curve c. And that curve is comes parameterized for us. That's pretty nice. So we'll get there in a second. So one thing we should know is that ds is equal to the magnitude of r prime times dt. So what we'll want here is to get that magnitude. So I want the magnitude of r prime. given again that r itself is negative t squared t. So r prime looks like it's going to be negative 2t1. So our magnitude ought to be negative 2t, that thing squared, plus 1 squared. Close the hat. And then this is now in terms of dt instead of ds. So it's, so s might just be a walk along this curve, but we're parameterizing our curve in terms of t. So we need to change ds over to dt. So we get that component, and I'll simplify it a little bit because I think that'll help us out. This looks like 4t squared plus 1 dt. So that's going to be our ds term, and we'll need to plug that into our integrand in order to get an answer. And then also we'll pay attention to this interval for t. It's between 0 and 1. Those are, so t starts at 0, ends at 1, which means our line integral should go from 0 to 1. So I'll plug that in for a and b. So if I then take a look at what our integrand should be, it's y times ds. Y is equal to t. So it's t times the square root of 4t squared plus 1. And then our dt is already written in wetword for us. It's there at the end. So that's the thing we got to integrate. And to do that, we'll need a u substitution. So let me just get one real quick. The thing on the inside of our square root is what I want to be. It's what I want to be u. So that's 4t squared plus 1, meaning that du is 8t dt. And if we'll notice that t that we have in there, we already have that because it was y. So 8t dt is our du, meaning if I go through to substitute some stuff over here, I really need the integral of, close enough. I want the square root of u du. But the element that I was missing out of du was that coefficient of 8. So I'm just going to have a 1 over 8 right there. And I'm going to bring that to the outside of my integral. But this integration is pretty nice. Just need to integrate u to the 1/2. So this is 1/8 times 2/3 u to the 3/2. Let's mark that in red again. So I know I've got a substitute here. And then I like to substitute back in for my original variable so that I can continue to use my original bounds. So that's what I'm going to do here. I'm going to substitute u back out of this equation, bring my t back in. 1/8 times 2/3 gives me 1 over 12 times 4t squared. Bring my t back in, plus 1. That goes to the 3/2 power, and we're evaluating from 0 to 1. So if I go to plug that stuff in, this is going to be 1/12. 1/12 times, when I plug in 1, 4 times 1 is 4, plus 1 is 5, to the 3/2, minus, plug in 0, 0 plus 1 is 1, to the 3/2 is still 1. So in the end, that's my solution. 1 over 12 times 5 to the 3 halves minus 1. Okay. So let's take a look at this next one. Okay. And I'm going to draw a coordinate axion here, or at least best I can do at one. Yeah, close enough. And talk about what we're doing. So we want to evaluate the line integral 6x squared dx plus 2y squared dy. Right. Evaluate the line interval giving the following steps, because our original integral is actually not a line integral. Or wait, is it? No, never mind. Take that back. I'm thinking too many sections ahead. That integral is indeed a line integral. We know it's a line integral because we're integrating along the curve or along the line C. Cool. This is not in the form that maybe we always see it in, because it's currently in its scalar form instead of in its vector valued form. And we're going to need to use the vector elements in order to figure out what that line integral should look like. So we want to convert this line integral over to, so it's currently an integral with two variables in it. It's got that multivariable element going on. We'd like to convert that into an integral of a single variable, because that's a lot easier for us to do. So that's what we're going to use the vector values for. So what are we doing? We have a circle, x squared plus y squared equals 16. So circle centered at the origin, it's got a radius of 4. And we're going to be going counterclockwise from 4 to 0 to 0, 4. So it'll be helpful to identify those points. So 4, 0 is along the x-axis. 0, 4 is along the y-axis. And we're told we're going to start here at the blue point, end up here at the red point. And we're going to travel along a circle in order to get there. So this is our path along the curve C. That's what we're doing. We're traveling along that path to get from 4, 0 to 0, 4. Cool. So what does it want us to do? First, we should parameterize that curve. And then we should make some substitutions to find a new integrand, one that will integrate over just t instead of needing to integrate over x and y. And then complete that integral. That's our goal here. So let's do it. If we're trying to parameterize a circle, the easiest way to do that is going to be with polar coordinates. If we try to use our rectangular coordinates, things get messy. We're going to need some like square roots, possibly some plus or minuses in there. Rectangular coordinates aren't great at parameterizing circles, but polar coordinates are. So I'm going to use a polar coordinate model in order to parameterize this thing. So I want r cosine theta and r sine theta. So let me start making some notes over here. So think polar coordinates. X is r cosine theta, and y is r sine theta. So that's gonna be my plan. Is using a polar coordinate model to parameterize this circle. So we have a fixed radius for our circle. It's always 4. So we're just gonna let r be 4. Theta is the thing that's gonna change. We're gonna run through some angles here. So I'm just gonna let theta be t. T for theta. Meaning my parameterization is gonna be 4 cosine t, 4 sine t. Once again, I'm considering t as theta, or theta as t, either way. So yeah, so I'm thinking of t as an angle rather than an x or a y coordinate. So with that in mind, if I'm looking for the bounds on t, I should be looking for some angles here. So my starting position is along the x-axis. That's an angle of 0 radians. So my initial t value is going to be 0. My ending position, which was 0, 4, that's on the positive y-axis. It's an angle of pi over 2. So that's where I'm going to get my bounds from. We're going to be those two angles, the angle to my starting point and the angle to my final point, my ending point. So 0 to pi over 2, I'm just doing that quarter circle, or that quarter circle arc. That's the curve that we're going along. Now that we have a parameterization, we can start making some substitutions over here. We'll get the easy parts out of the way. A and B, we already know what they are. A is 0, B is pi over 2. Same as we just found as our bounds for t. So I need to substitute for x and y, which means also substituting dx and dy. So I already have my x and y. Those are the parameterizations. I should calculate dx and dy. So dx, that's the derivative of 4 cosine t. That derivative is negative 4 sine t. dy then is going to be the derivative of 4 sine t, right? So I'm getting this dx and the dy from my parameterization, right? My parameterization tells me what x and y are. I need to take derivatives of both of those. So dy, and I'm forgetting an element over here, aren't I? Should be proper about this. 4 sine t dt. That bit's important. Dy, the derivative of 4 sine t, which is 4 cosine t dt. And so I should be adding those dt's in there. WebWorks going to take care of that for us. It's got the dt already typed in. We just have to put the integrand part in. So that integrand is 4x squared, 6x squared dx plus 2y squared dy. So that looks like 6 times 4 cosine t squared times negative 4 sine t. And again, dt, but I'm factoring that bit out, putting it all in at the end. Plus 2 times 4 sine t, that bit squared, times 4 cosine t. So that's my integrand. This bit goes right there. All right. At this point, my integral is all set up. All I have to do now is evaluate it. So let's leave that line on so that we can do it. Yeah, let's take the time to actually integrate this thing out. It'll probably be worth seeing. So I want the integral from 0 to pi over 2 of that whole thing. You know what? I am going to speed up the process a little bit, though. Give me a control. Hey, come on. Control C, control V. Yeah. I already wrote it down once. Don't need to write it down again. And all this gets a dt plonked down at the end. dt. All right, so we integrate this thing, and we have a very nice u du situation going on. If both of our green parts are their respective u's, the parentheses in purple and yellow that come after them are their du's, which is pretty nice. So that just means I'm going to have a u cubed plus a u cubed term with some other coefficients going on. Let's just make sure we get those right. So this is going to be a 6 over 3 times 4 cosine t cubed plus 2 over 3 times 4 sine t cubed. And we'll be evaluating between 0 and pi over 2. So this thing is equal to, big parentheses, 6 over 3. I'm going to plug in pi over 2 first. Cosine of pi over 2 is 0. So 6/3 times 0 cubed plus 2/3 times sine of pi over 2, which is 1. Don't forget the 4 that's in there. 4 cubed. Close those parentheses. Minus another big set of parentheses. 6/3 times cosine of 0, which is 1. Don't forget the 4 that's there, though. So 4 cubed plus 2/3 times the sine of 0, which is 0. Cubed. Close the second big set of parentheses. That's what we get when we plug everything in. Now let's just evaluate that bit. Well, while my pen needs a minute to like cool down. Hey, what does this? Hey, cut it out. Well, if you're thinking ahead while I'm fixing my pen one more time, I eventually get to an answer of negative 256 over 3. Following along the steps I used to get there, I end up with a 2/3 times 4 cubed minus 6/3 times 4 cubed, which gets me to a negative 4/3 times 6 cubed, and 6 cubed is 64. 4 cubed is 64. Blah, 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 blah. And then 4 times 64, or we could think about it 2 squared times, or 4 times 4 cubed, which is 4 to the 4th, or 2 to the 8th. 2 to the 8th is 256. If you're doing the mental math to get there. But yeah, negative 256 over 3. All right, I think I've got one more problem that I want to do all out. So let's take a look at it. The fundamental theorem of line integrals, the last section that we cover on the exam. So what do we want to do here? Find a function f such that the gradient of f is equal to that expression. And then we're going to use that function to evaluate the integral of the gradient f dot dr. And we're going to use the fundamental theorem of line integrals in order to do it. So what it says is that what the fundamental theorem of line integrals says is pretty similar to the fundamental theorem of calculus, just adapted to line integrals. In particular, this fundamental theorem is going to be important when we get into the particularly nasty sections at the very end of the course. I'm talking like after exam 3. All of that stuff is going to be building on the fundamental theorem of calculus to adjust it up into multivariable calculus. So this is the first stab that we're going to take at upscaling that fundamental theorem of calculus. First thing you want to do is just upscale it to line integrals, because line integrals are very similar to the integrals we already did in Calc 1. They're just going to be done over a curved line in 3 space instead of just a flat line in 2 space. Or actually, at that point, we're just considering it a one-dimensional flat line. But I digress. What the fundamental theorem of line integrals says is that if we can integrate the gradient of f between 2 points, that'll be the same as simply evaluating the original function at those 2 points and taking a difference. So it's basically saying that the integral of df between a and b is equal to f of b minus f of a. So that's what we had from fundamental theorem of calculus. It's the thing you do every time you evaluate a definite integral. You just plug in the top number, plug in the bottom number, take the difference. We did it in the previous problem there. That's the fundamental theorem of calculus. We're going to adapt it to line integrals. So let's do that. We want a function so that the gradient of f is equal to the function provided. So what that means is that if I were to integrate each of those 3 pieces back, it should tell me something about my initial function. So let's give that thing a shot. I want to integrate each of my 3 components back up. Because the gradient takes the derivative with respect to each position, it's like the first coordinate is the x partial, second coordinate is the y partial, third coordinate is the z partial. I want to integrate those variables back up. So I'll integrate the x partial for x, I'll integrate the y partial for y, I'll integrate the z partial for z, and see what I get when I bring it all back up. So integrate negative 2y z e to the x z. I don't know why sometimes I say z and sometimes I say z. It's kind of how I'm feeling at the moment, I guess. I want to integrate that with respect to x. Then after that, I'm just going to set up each of the 3. After I do that, I'm going to want to integrate the y component. So negative 2 e to the x z dy. And then I'm going to integrate the z component. Oh, I'm really switching it up. Integrate the z component. Nope. All right, fine. Negative 2 xy e to the xz dz. So I'm going to integrate each of those 3 pieces and see what I get. So integrate the x component, and I'm going to get negative 2y e to the x z. And then I'm going to add in a plus c, because there could be some extra stuff going on here. This plus c isn't necessarily a constant. That plus c could contain a constant number, could also contain any function that depends, or any term that depends only on y and or z. because if there were a term that depended only on y or z or both, the x partial would have gotten rid of it, and I couldn't integrate back to it. So we're gonna put that right there. We'll integrate the y component. There is no y present, so this just becomes negative 2y e to the xz. Throw in a plus c. Again, that plus c could have more than just a constant, could also have terms with x or z, just nothing with y in it. And the last one, integrate, I'll get negative 2y e to the x z, again with a plus c going on. So what I would want to do here is compare each of these three pieces, each of the three things that it integrated to, and any unique term I'm going to get added into F. This particular case was kind of boring. They all integrated to the same thing. So that's our function. Our function must be negative 2y e to the xz. I already had it written in. Fancy that. I think we'll look at an example here in a minute that's got some stuff that it gets more exciting. But here, if they all integrate to the same thing, then that must have been our original function f. So what is up? What is up next? I need to look at t equals 0 and t equals 1, because that'll be important. Because I don't really get to integrate from 0 to 1. I want to be integrating from point to point, which means I need to find an A point and I need to find a B point. So A is going to be R of 0, R of 0. And that gets me the point 2, negative 5, 0. I should also get a B point. It's R of 1. And plug in 1. What do we get? 3, negative 4, 0. So then in the end, what I want to say up here is that this line integral of the gradient of f dot dr is equal to f of b minus f of a. That was the whole point of doing it this way. So I don't actually need to, plug in the parameterization parts into each of x, y, and z, or find dr. I don't need any of that because I know that the function I'm integrating is the gradient of some scalar function that it came from. This vector valued function that I'm integrating is the gradient of some scalar function f. So I can use the fundamental theorem to solve it instead of the more direct method, which we did in the previous problem. And we'll see that the math works out significantly nicer. I don't have to do all that crazy stuff up there of plugging stuff into those exponentials. No. All we have to do is plug things into f. So I want f of 3, negative 4, 0 minus f of 2, negative 5, 0, which is negative 2 times whatever I get when I plug in 3, negative 4, and 0. Negative 2 times, or what? Blah, blah, blah. Yeah, right. I already knew all of that. I already had the negative 2 there. Y is negative 4. E to the 0 is 1, so that's negative 4. Minus the other point, which ends up being a negative 2 times, plug some stuff in, 5 times e to the 0. So still -5. Altogether, that's -2. Yep, so way nicer to evaluate our line integral this way. Maybe I should just kind of plug in what I'm actually doing there. This is -2 times -4 times e to the 3 times 0 minus -2 times -5 e to the 2 times 0. That's the work I was doing. But anyway, I get -2. That was way nicer than having to actually do that line integral. So fundamental theorem ends up being pretty fundamental. Yeah. Sorry, I won't do that again. Let's see. I've got a few more problems here at the end where I've already done them up because I just want to talk about specific elements of them rather than the problem as a whole. Don't want to look at a few individual pieces. Jumping back to the max and min values problem. Let's see what we've got here. Finding the absolute maximum minimum values of function provided on the set D, which is the triangle sketched out below. So what I did here, following the steps that it takes to find absolute maximum and minimum on a function, is I found a critical point first. That's the green one right in the middle. Then I've got 3 different boundaries that I'm going to have to check. I've got the left edge, the top edge, and the bottom edge, right? Each of those lines I'm going to consider an individual boundary. So I'm going to parameterize each boundary so that it's just one equation. Those equations being, looks like x equals 0 is the equation of the left line. I've got y equals 7 minus 7/8 x for the top line, and y equals 7/8 x minus 7 for the bottom line. But I've got equations for each of those. I'll substitute them into f so that it becomes a function of only one variable, and then find critical points on each of those 3 boundary lines. Those are the blue, pink, and purple points. Those are the critical points I came up with. Then finally, I also need the boundary values, which are the boundaries of each of those lines. And because the lines all overlap, there are a total of only 3 boundary points, since each boundary point will be the boundary of 2 lines. So they were the initial boundary points listed in the beginning: 8, 0, 0, 7, and 0, -7. Yeah, and so the way that I found the bottom line, so that purple equation, the one that I'm going to need on the boundary, it's f of x, and instead of y, I have 7/8 x minus 7. So I'm just substituting for y right here. Oh, I wasn't on the screen. Let me say that again. So along the bottom, that purple expression I'm going to be using, my boundary, or the equation of my function along the purple boundary on the bottom, I'm replacing y with 7/8 x minus 7. So I just substitute it into the equation f and go from there. Well, yeah, here was a real fun one from the fundamental line theorem. So we say that so we had this component test form. So if we have some field that's P and Q, so some field, we say that it's a conservative vector field, which we need a conservative vector field in order to back that up. Okay, so conservative vector fields. We say that a vector field is conservative if that field is the gradient of some scalar function f. So this is referring back to that very last problem that we did, where we integrated each of the x, y, and z components to find the original function f. that the vector field we were looking at was the gradient of a function. We can do a test before we do that to determine if that field is even capable of being the gradient of some function. We say that that field is conservative if if I can take the gradient of some function and get the field. And we say that the field is not conservative if I can't do that. An easy test is to look at, for 2 dimensions, if the opposite partial derivative of each component is equal to the other. So what I mean by that is take the x component and do a y partial, then take the y component and do an x partial. So swap the partials that we're doing there, which is a little bit confusing if you say it all that way. But if you think about where this function is supposed to come from, I think it'll make more sense. So since I want my field to already be some sort of gradient, that means the x component already has an x partial done, and the y component already has a y partial done. Because again, this is coming from some original function, little f. So x component already had its x partial, y component already had its y partial. If I want to see that this field is conservative, that means that the mixed partial terms must be the same. So the xy partial has to be equal to the yx partial, because it should not matter which order I do my partial derivatives in. So since the x partial already has its x component already has its x partial done, I should now do its y partial because it hasn't had that one yet. The y component has already had its y partial done, so now I should do an x partial because it hasn't had that part done yet. Then I compare xy partial to yx partial. If they're the same, great, conservative vector field. If they're not the same, that means that our original assumption that the first thing already had its x partial done and the y thing already had its y partial done must have failed, because they did not come from the same function if those mixed partial terms aren't equal to each other. So that's what this conservative vector field stuff is trying to get at in this problem. And what we're going to do then is upgrade or upscale that 2-dimensional test to a 3-dimensional test. So what we have to do is just check all 3 mixed partial terms. In 2 dimensions, we've only got the one mixed partial term, x and y, but in 3 dimensions, we've got all 3 combinations of 2 variables. So we need to check the xy partial terms, we need to check the xz partial terms, and then we need to check the yz partial terms. That's what that highlighted piece in the middle is saying, although it's got a whole bunch of letters and symbols that get a little, they can get confusing if you just look at letters without like thinking about what it means. But again, every time we see a P, a Q, and an R, we should assume that those have already had one partial applied to them already. Q or P has already had its X partial, Q has already had its Y partial, R has already had its Z partial. So we'll compare each one of those. So that's what I decided to do over here. Instead of calling it P, Q, and R across the top, I'm going to call it fx, fy, and fz, because that's really what I want them to be. I want P to be fx. I want Q to be fy. I want R to be fz. And then what I'll do is I'll just look at its other partial derivatives. Fx, I started there, so I should do a y partial and I should do a z partial. Y partial, I get 2, z partial, I get 0. For starting from the y partial, I should do an x partial and a z partial. Again, I get 2 and 0. For the z partial, I should then do an x and a y partial. I get yz or xz for those 2 options. Then I just need to compare every pair of terms that has the same 2 partials. So looking across xy and xy, both of those are 2. If I go to find the 2 spots that have xz, I'm looking lower left and upper right. In one case, I get 0, but in the other case, I get yz. Those 2 partial derivative terms don't match up. So this thing is not a conservative vector field. I can also do the same thing for the yz. So bottom, middle, and bottom right, I get 0 and xz. Again, they don't match up, so they don't work out. So if I take a look at this spot down here at the bottom, check all of the requirements of the extended component test that fail, making the integral path dependent. And I would say that it's the xz and the yz components are the ones that end up failing the test. Because it's really every time the z partial bit gets involved, it fails. Another way of thinking about that, if we bring it back to the problem that we were working on, the very last one we did as a group, I want to integrate the x partial, integrate the y partial, integrate the z partial, and see what I get. And I end up getting a few terms that just cannot coexist. I get 2xy for the x partial, I get 2xy for the y partial, but then I get xyz squared over 2 for the z component. That's z partial integral, which means that there's no way that those terms can be compatible, because if this thing were a conservative vector field, I should have seen this z squared element show up in both the x and the y partial derivatives, because that z squared is attached to both an x and a y factor. So it's that last bit that makes this thing not a conservative vector field. So all that means when we say that making the line integral path dependent is that the line that I take to get from point A to point B matters. In a conservative vector field, it doesn't matter what path I take. It only matters where I start and where I end, which is when we can apply the fundamental theorem of line integrals. So there's a whole heck of an explanation that might have been more than you bargained for. But hey, it might help. So we went over it. Okay, this next one, back to maximum minimum values. I just want to talk briefly about the test to see if something is a local maximum, a local minimum, or neither. And it all comes down to this determinant that we want to talk about. Determinant or discriminant, it's one of those two words. I always get those mixed up. So that discriminant term or determinant term, whichever one it is, D, capital D, it's the two single variable second derivative terms multiplied together minus the mixed partial second derivative term squared. So the double x partial times the double y partial minus the xy partial squared. And we're going to use that to test if something's a local minimum or a local maximum, specifically a critical point. Test of a critical point is a local minimum or a local maximum. And so what we need here in order to make this thing become a local minimum or a local maximum is for D to be positive. So if we think about what's going on in that D thing, I've got my mixed partial derivative term squared and I'm subtracting it away. Don't much care beyond that. It's a positive number that I'm going to be subtracting from this other bit, but mostly I'm going to be ignoring the mixed partial. I want to focus for a moment just on the two single variable second derivatives. So if I'm multiplying if this thing is going to be positive, I must have both single variable second derivatives have the same sign, because I need fxx times fyy to be positive. Because if it's not positive, I'm going to end up with a negative number for D. And I need both of those two second derivatives to have the same sign in order to have a local minimum or a local maximum. Because what that's effectively saying is that the concavity around my critical point must have the same sign in order to be a local minimum or a local maximum. I either need to be concave up in both the x and y directions or concave down in both of the x and y directions. And if I don't have that, it's going to be a saddle point, or neither a local maximum nor a minimum. So I need to have both of those terms have the same sign And what that means is that this D equation must come out positive if they're going to have the same sign. So from there, if I get that they're the same sign and D is positive, great. D being positive means I have either a maximum or a minimum there, because that D being positive only means they have the same sign. It hasn't yet told us what sign they have. So once I know they have the same sign, I need to check either sign to find out if I have a maximum or a minimum. I already know that they have the same sign, so checking either the second x partial or the second y partial will work. But I just need to check one of them to find the concavity. If it's concave up, I have a minimum, and if it's concave down, I have a maximum. That's what that second derivative test is saying. Feels like it's worth talking about that right before this exam. Meaning we could classify a minimum or a maximum as long as we have those three partial derivative values. Because yeah, as we can see here, D comes out to a positive number. It's 11. It's greater than 0. And I get that both the x partial and the y partial, the x second partial and the y second partial are both positive, meaning it's concave up in both directions. This is what makes it a minimum. The test says you always have to check the second x partial specifically, but you don't. You can check either the second x or the second y partial. But textbooks being what they are, it only put one option. Something else out of a line integral. What I want to talk about here. Oh, the the Harry Potter problem. Right. Thought this was just a good one to look at. So if we're trying to find the total number of mosquitoes that Harry Potter runs into while he's flying around his loop-de-loop, we're going to want to integrate the mosquito density function. So integrating the density function will get us up to the number of mosquitoes that he runs into. And then I just thought, running through the algebra on this one wasn't too bad. If you want to follow along with the work, here it is. Not a whole lot I really want to say here, because we already covered a line integral. We need to define the magnitude of r prime. We'll multiply it into our density function, and then we integrate between our bounds, which is 0 to 5. Cool. And with that, I do believe that now has taken me to the end of everything I had prepared. Oh, wait. Nope, there's one more that looks like it didn't make it in. Hang on one second. Let me go paste in the missing problem. One last thing I wanted to do, identifying some vector fields. Right here. So problem 2 out of section 17. So given some vector field mappings, match a function to its corresponding vector field. Gradient vector fields. Yeah, that makes more sense. Say, wait, functions don't have vector fields. Gradients do though. So what I do is I take the gradient of each of those 4 functions, 1 through 4, and then I'm going to start looking at where I think they belong. So what do we get? If I were to start investigating a few things, what did I think was worth doing? Let's start with D. D is interesting because its y component is just x. I thought that was going to be an easy one to start identifying what its vector field would look like. So looking at just its y component, I'm going to look up and down the y-axis because I should see an interesting pattern show up because the y component is just equal to x. If I look up and down that y-axis, the further up the y-axis I go, I should have a longer vector field pointing right, which is what I'm getting along that yellow highlighted section. Wait a minute. Let me back that up. The y component depends only on x, which means if I look up and down the y-axis, here we go, this is the writing. Okay, y component depends only on x, which means if I look up and down the y-axis, I have an x value of 0. So every vector along the y-axis should only point left or right, because the y component of that vector is 0. Again, that y-axis is the line x equals 0, which means every vector along the y-axis has has a vertical component of 0. So they only point left and right, which is how I'm going to identify D as graph number 4, vector field number 4. Another helpful hint is looking at places where the vector is gonna where this vector field is gonna have some 0 values. So looking at number 1, 2x plus 2y, if I take y equals negative x as a line, I'm going to get 0, 0 for both elements of my vector field. So along the line, y equals negative x, I get 2x minus 2x for both components, so it's just 0, 0. So if I look along the line, y equals negative x within that vector field, I should have a whole bunch of 0 vectors, which is exactly what I see in graph A. I have the line y equals negative x that shows up. It's pretty easy to pick out of that vector field because there's a whole line where every single vector is 0. So that one I thought was helpful to identify. Then looking at the others, 3 is a relatively easy one. Its gradient vector is just xy times 2, but like who cares about the 2? Just ignore that. It's not all that important. The vector field looks like xy, and xy is just an exploding vector field outward from 0. Every vector in the vector field xy just points away from 0 because it's just the position vector. So C must be 3 because of the way that those vectors are pointing. And then we have number 2. So number 2, kind of similar to number 3 in that the vector field is still xy, but it's also got an extra magnitude being attached to it. So we should still see some vectors that either point in or out of the origin, but with some cosine element thrown in, we might see, those magnitudes changing as we move outward. Might even see some kind of a circular pattern show up, but number 2 is going to get matched to graph B, because again, they're all pointing either in or out of the origin, but the magnitudes change as I move around. But the directions again are always still either in or out of the origin. All right, and that is the actual last problem we're going to talk about. So with all of that, good luck on this exam. Thanks for sticking around for a whole, wow, it was a 2.5-hour video by the time we got this far. And so unless I think of something else I want to talk about before I wrap things up with everyone that's here live, this is where we'll be ending things. So again, good luck on exam number 2.